Right. So today I'm going to be explaining this important paper with the title Permutation Invariant Graph Generation via Score-Based Generative Modeling. This AI stats paper in 2020 from Stanford University. Learning generative models for graph structured data is challenging because graphs are discrete, combinatorial, and the underlying data distribution is invariant to the ordering of nodes. However, most of the existing generative models for graphs are not invariant to the chosen ordering, which might lead to an undesirable bias in the learned distribution. To address this difficulty, we propose a permutation invariant approach to modeling graphs using the recent framework of score-based generative modeling. In particular, we design a permutation equivariant multi-channel graph neural network to model the gradient of the data distribution at the input graph. This permutation equivariant model of course, some of the permutation equivariant models, you lose expressivity. Of course, it provides permutation equivariance, but you lose expressivity. That's why there are many other paradigms that are alternative to these that I will explain in a different video. So this permutation equivariant model of gradients implicitly defines a permutation invariant distribution of graphs. We train this graph neural network with score matching and sample from it with annealed version of the Langevin dynamics. We first demonstrate the capacity of this new architecture in learning discrete graph algorithms. For graph generation, we find that our learning approach achieves better or comparable results to existing model benchmarks. So just a background on score-based generative modeling. So we have a data distribution and we have this noise distribution Q sigma, and a sequence of noise level, sigma 1, sigma 2, until sigma L. L different noise level. That's why our summation is over that. We want to see, because a score at different noise level is different. So we train a noise conditional model, which is a neural network that is parameterized by the theta parameter. To approximate the score function corresponding to noise level sigma. So after the conditional score model has been trained, we use annealed Langevin dynamics for sample generation. We use this. So this is the background that I have explained several times. Contrary to the weighted graphs we use to define the probability density, in real-world problems, unweighted graphs are much more common, which means entries in the adjacency can be either 0 or 1, while the score-based method was initially proposed for handling continuous data. It can be adopted to generate discrete ones as well. So we first show our modification of score-based generative modeling for graph generation, and then introduce our specialized neural network architecture for the noise conditional model. This is the noise distribution. We add Gaussian perturbations to adjacency matrices and define the noise distributions like this. So we only add Gaussian noise to the upper triangular parts of the adjacency matrix because we focus on undirected graphs whose adjacency matrices are symmetric. So the training loss becomes this. So expectation is over the sampling process defined here. And note that the supports of the noise distribution spans Rnn because we have n number of nodes. So to generate a tilde, we first sample n, which is the number of nodes to be generated, and then sample a tilde with annealed version of Langevin dynamics. Then we update a tilde by iteratively sampling from a series of trained conditional score models using Langevin dynamics. So now we want to focus on this permutation invariance, permutation equivariance, and also invariance. Permutation invariance is a desirable property of graph generative models since the true distribution is inherently permutation invariant. We show that by using a permutation equivariant score function, the corresponding distribution is permutation invariant. So if S is a permutation equivariant function, then we can define this scalar function. You know, S of x and dx in the Frobenius norm, Frobenius inner product. So it's a scalar because it's just a trace of this transpose this. And then if you integrate, then again is a scalar. So this is a scalar function. Look at this. This is a scalar function. The theorem says that this scalar function is permutation invariant. And the proof is in the appendix of this paper. So since the gradient of log likelihood estimation is permutation invariant, the implicitly defined log likelihood function is permutation invariant. So according to theorem 1, given below by the line integral of f theta, and then they talk about multi-channel GNN layer to implement it. For a C-channel GNN, we have this M message passing steps. So after M message passing steps, we just concatenate them, and then we use multi-channel GNN of A and C IN. The EDP GNN layer is the key component of our model. It transforms the input adjacency matrix to another one, allowing us to adaptively change the process of message passing. So first, we use node feature inference using a multi-channel GNN to encode the local structure of different channels of the graph into the node features. We have then edge feature inference. We update the edge feature inference, if you look, it's based on your Z node feature inference and adjacency here. So we have edge feature inference, updating the feature vector of each edge based on the current features of the edge. Now this MLP is a multi-layer perceptron. But to ensure symmetry, the new adjacency matrix is given by this. A matrix with its transpose, so it's A. And to get the output, we employ a similar approach of this reference where we aggregate information from all previous layers to produce a set of permutation equivariant edge features. But your node features are initialized like this. So it's just summation of adjacencies for if you fix one node and then summation over the all edges that are connected to this node. Then we use the following initialization for each node. So our F theta is MLP of concatenation of A. So this figure shows the EDP GNN with 3 layers. The input is an adjacency matrix, and the output are edge representations. Now they talk about noise level conditioning. The framework that I explained in the previous video requires a core network condition and a series of noise levels. And we hope to provide the conditioning and noise levels with as few extra parameters as possible. To this end, we add gains and bias terms, condition on the index I of the noise level sigma I in all MLP layers, and share all the parameters across different noise levels. A conditional MLP layer for your score function is like this. So this alpha I, beta I, you should learn this for each noise level sigma I. And then they talk about permutation equivariance of EDP GNN. And these are the sampling from training data. Then in the appendix they talk about the hyperparameters, those noise levels that we discussed in the previous video. And these are extra samples from training data on the lobster graph dataset.